Hello all. In my previous class, I discussed current density in a conductor, right? And also temperature effect on mobility and conductivity, Fermi-Dirac function. Now in this class, I will discuss about chapter 2, that is semiconductor material, right? So here first I can classify the semiconductor materials based on doping or concentration actually. That is intrinsic semiconductor and extrinsic semiconductor, right? You know, this intrinsic semiconductor also called as pure form of semiconductor, and this extrinsic semiconductor also called as impure form of semiconductor, impure form of semiconductor, right? So why it is named as impure form of semiconductor? Because here impurities added to the pure form of semiconductor. You know, adding of these impurities to the pure form of semiconductor is called as doping, right? You know, the doping can be done in two ways. One is the diffusion process and another one is ion implantation, right? Here, because of this adding of impurities, this extrinsic semiconductor offers high conductivity, right? It offers high conductivity means what about the intrinsic semiconductors? Actually, it offers low conductivity, right? Now coming to the examples of intrinsic semiconductor, that is silicon or germanium, and coming to the example of extrinsic semiconductor, that is n-type or p-type semiconductor. This is about classification of the semiconductor material, right? Copy. Yeah, completed. Next topic, intrinsic semiconductor. Copy this figure. Copy these two figures first. Yeah. See, intrinsic semiconductor. You know, this intrinsic semiconductor is formed with fourth group elements like silicon or germanium. Okay, and it has 4 valence electrons. These 4 valence electrons are involving in covalent bond formation, and also these 4 valence electrons are strongly bonded with parent atom. Okay, such electrons are called as bounded electrons. Right? You know what is bonded electron actually? Bounded electron is nothing but electron present in covalent bond. This is with respect to bond model, right? And same way with respect to band model, what is the bounded electron actually? Bounded electron is nothing but electron present in valency band. Valency band. Actually, any material can be explained or can be analyzed in 2 ways. One is band model, another one is bond model, right? So this is the bond model, and previously I explained the classification of the material in our first chapter. Okay, that is with respect to band model, right? Now here, bound electron is nothing but electron present in covalent bond or electron present in valency band, right? Now here at T equal to 0 degrees Kelvin, at T equal to 0 degrees Kelvin, actually all electrons are behaves as a bounded electrons. If all electrons are behaves as a bounded electrons, then conduction cannot possible. If conduction cannot possible, we can say, okay, the intrinsic semiconductor acts as a insulator at what temperature? 0 degrees Kelvin, right? Write down the notes. Write down. These are formed with fourth group elements like silicon or germanium, and it has 4 valence electrons, These 4 valence electrons are involving in covalent bond formation, and also strongly bounded with parent atom. Such electrons are called as bounded electrons. Yeah, underline bounded electron. Next point, bounded electron is equal to electron present in covalent bond or electron present in valency band. Yeah. Next point, at T equal to 0 degrees Kelvin, all electrons are behaves as a bounded electrons. So that conduction cannot possible. Hence, intrinsic semiconductor acts as an insulator. At T equal to 0 degrees Kelvin. Yeah. Now underline Intrinsic semiconductor acts as an insulator at T equal to 0 degrees Kelvin. Right. Now, next point. Listen. Now temperature is increased. Right. If temperature is increased, what happens? Thermal energy is supplied to these valence electrons. After acquiring sufficient thermal energy, the valence electrons can move into interatomic space and it can produce what actually? And it can produce free electron hole pair. This process of producing of free electron hole pair due to thermal energy is called as what actually? Thermal excitation. Right? Now, I am going to define a free electron. What is the free electron actually? The free electron is nothing but electron present in interatomic space. Interatomic space. Or electron present in conduction band. This is with respect to band model. This is with respect to bond model. Right? Now I can also define the hole. Hole is nothing but incomplete covalent bond actually. Okay. So simply hole is nothing but what actually? Vacancy in the hole is nothing but the vacancy in the covalent bond or the vacancy in the valency band with respect to band model. Right? Now write down. Write in notes. When the temperature is increased, thermal energy is supplied to the valence electrons. Thermal energy is supplied to the valence electrons. After acquiring sufficient thermal energy, the valency electrons can move into interatomic space and produce free electron hole pair This process of producing of free electron hole pair due to thermal energy is called as thermal excitation. Yeah. Underline thermal excitation. Yeah. Next heading free electron. Electron presenting conduction band. Or electron presenting interatomic space. Yeah. Next point, hole equal to vacancy in covalent bond or vacancy in valency band. Right. Now, see, when the temperature is increased more, what happens? See, when the temperature is increased more, actually, so more number of covalent bonds can break. And it can produce more number of electron hole pair. Right? But these electron hole pair having a random motion due to thermal energy. Due to this random motion of free electrons, actually, what will be the net current? 0. Right? If net current equal to 0, then what should we do? Then we can apply external electric field. Right? See, because of this external electric field, what happen actually? Okay, the electrons can move in interatomic space. Which electrons actually? The free electrons. The free electrons can move in interatomic space and it can produce a current. That current is called as what actually? Free electron current. Yeah. Similarly, due to this applied external electric field, okay, electrons can move in covalent bonds. Which electrons can move in covalent bonds actually? Bounded electrons. and it can produce a current. That current is called as hole current. But this hole current is due to bonded electron, right? Now that means in case of semiconductor, what will be the total current actually? The total current is nothing but IN plus IP, that is free electron current plus hole current, right? Write down notes. When the temperature increases further, when temperature increases further, then more covalent bonds can break and produce more number of electron hole pairs. And produce more number of electron hole pairs. Electron hole pair. Right? Now, when an external electric field is applied, next point, when an external electric field is applied, then due to this applied external electric field, free electrons can move in interatomic space and produce free electron current in bracket IN. Yeah, please underline free electron current. Yeah. Next, similarly, due to applied external electric field, electrons can move in covalent bond. In bracket bonded electrons and produce hole current in bracket IP. Next point, hence the total current is given by I total equal to IN plus IP. I total equal to IN plus IP. Right. See, this is the in terms of current. What is the same equation in terms of current density actually? J total. What is current density? Current per unit area, right? So J total equal to Jn plus Jp. What is this Jn actually? Current density due to free electrons, right? What is the equation of free electrons actually? Current density to free electrons. For free electrons actually, this current density is nothing but N into E into mu N into E. This is already we derived, okay? Current density in a conductor. In conductor actually, current density is due to only one type of charge carrier, that is free electrons. But whereas in semiconductor, the current density is due to two types of charge carrier, that is free electrons as well as holes, right? The same derivation is applicable to here also. Directly here I am writing Jn equal to N into E into mu N into E. Similarly for holes, what will be the Jp here actually? The Jp is nothing but P into E into mu N into E, right? Where P is nothing but the hole concentration, right? Here N is nothing but electron concentration. And mu N comma mu P, this is mu P. Mu N comma mu P is nothing but mobility of free electron and hole. And I think we know E is nothing but applied external electric field, right? Now here, what will be the J total here actually? The J total equal to, so N into E into mu N into E plus P into E into mu P into E. Now, common here, N into E into mu N plus N into E into mu P into E. This is the J total value. If you compare with this, J equal to sigma E, right? Now what is the conductivity? Conductivity, that is N into E into mu N plus P into E into mu P. This is the conductivity for what actually? Semiconductor. This is the conductivity for any semiconductor. For any semiconductor means the semiconductor is intrinsic or extrinsic, right? Now I can define for intrinsic semiconductor. See, for intrinsic semiconductor, first of all, what is the condition actually? The condition is N equal to P equal to Ni. Right? This is the condition for intrinsic semiconductor. Means in case of intrinsic semiconductor actually, so it has equal number of electrons as well as equal number of holes, that is represented with Ni, whereas Ni is nothing but intrinsic concentration, right? Now what is the conductivity for intrinsic semiconductor actually? That is sigma I. Okay, this Ni is nothing but Ni into E into mu N plus P is nothing but Ni into E into mu P. Now the sigma I is nothing but common Ni into E into mu N plus mu P. This is the conductivity for intrinsic semiconductor, right? Copy? Yeah. Write down where Ni is the free electron concentration or hole concentration, that is intrinsic concentration, nothing but intrinsic concentration. Actually, intrinsic concentration is nothing but where free electron concentration or hole concentration. Next, mu n comma mu p are the mobility of free electron and hole. Mobility of free electron and hole. Right. Next, note. See here, mobility of electron is greater than mobility of hole. Why? The question is, mu n is greater than mu p. Why? Yeah, listen. Why mobility of electron is greater than mobility of hole actually? You know, in the whole current is due to what actually? Bounded electrons. The whole current is due to bounded electrons. Okay, but this bounded electron cannot move as like as a free electron, because here the free electron is moving in interatomic space. The bound electron is moving in covalent bond. Now which can is move freely? Free electron. That's why mobility of electron is greater than mobility of hole. Right? Right out. Very important one actually. Mu n is greater than mu p because whole current is due to bounded electron. Whole current is due to bounded electron, but bounded electron cannot move as free electron. Right. Next, write down one example question. in your classroom workbook, question number 1. Chapter 2, question number 1. Yeah. Write down a question. A pure silicon sample has Ni equal to 1.5 into 10 power 10 per centimeter cube. 1.5 into 10 power 10 per centimeter cube. Comma, mu n equal to 1300 centimeter square per V second. 1300 centimeter square per V second. Next, mu p equal to 500 centimeter square per V second. Calculate first bit conductivity, second bit resistance of the sample, if L equal to 1 centimeter, and cross-sectional area of sample is 10 power minus 2 centimeter square. 10 power minus 2 centimeter square. Right. Now, what is the given data actually here? Did the question once? The given free electron concentration, intrinsic concentration is nothing but 1.5 into 10 power 10. And mobility of the free electron, that is 1300 centimeter square per volt second. And the mu p is nothing but 500 centimeter square per volt second. Right? Here, what is the first bit? What we want to calculate actually? Conductivity. Right? Here, conductivity of what? Conductivity of intrinsic. A pure silicon sample is nothing but it's an intrinsic sample actually. See, conductivity of intrinsic semiconductor. What is the formula for conductivity of intrinsic semiconductor actually? Ni into E into mu n plus mu p. What is Ni here actually? Ni is nothing but 1.5 into 10 power 10. Charge of electron 1.6 into 10 power minus 19. Mu n 1300 and mu p is nothing but 500. Right. Now what is this value actually? This is 4.32 into 10 to the power of minus 6 ohm centimeter whole power inverse. This is the conductivity. Right. And what is the next bit? Resistance of the sample. Right. What is the formula for resistance actually? Rho L by A. What is the rho in terms of conductivity? L by A into sigma. What is L? The given 1 centimeter cross section area, that is 10 power minus 2 sigma I, intrinsic conductivity. How much? 4.32 into 10 to the power of minus 6. The value is 23.1 mega ohm. This is the resistance of the sample. Right? Copy. Yeah. Completed. Next topic. Calculation of intrinsic concentration. That is in bracket Ni. Heading calculation of intrinsic concentration. Right. So now, see how to calculate the intrinsic concentration in a semiconductor. Right. First, before going to calculate actually, first I can define the intrinsic concentration. Intrinsic concentration is nothing but what actually? It is the concentration of free electron concentration or hole concentration. It is the concentration of free electron concentration or hole concentration is called as what actually? Intrinsic concentration. Right. Now, how to calculate this intrinsic concentration actually? Okay. First I can define for any semiconductor. For any semiconductor means that may be intrinsic or extrinsic. What will be the electron concentration equation? N equal to Nc into e power minus of Ec minus Ef by kT. This is the electron concentration in a semiconductor, right? Now this is equation 1. Next equation 2, that is hole concentration. So hole concentration is nothing but Nv into e power Ef minus Ev by kT. That is equation 2, right? So where Nc, Nvs are nothing but what actually? Density of energy states in conduction band as well as valency band, right? What is this? Energy states of conduction band and valency band, right? See, what are the Nc, Nv equations actually? Nc equal to 2 into 2 pi Mn into k bar T by h square whole power T by 2. Nv equal to 2 into 2 pi Mp into k bar T by h square whole power 3 by 2. Actually, these are the standard equations. We have derivation also, but here directly we are considering actually, right? What is this Mn, Mps actually? These Mn, Mps are nothing but effective mass of free electron and effective mass of hole, right? I think you know what is K and T bar, right? What is H square? You know Planck's constant. Okay. Next, to calculate the intrinsic concentration actually here, consider 1 into 2, right? 1 into 2 means N into P equal to Nc into e power Ec minus Ef by kT, Nv into e power Ef minus Ev by kT. Now Np equal to, what is Nc equation actually? 2 into 2 pi Mn into k bar T by h square whole power 3 by 2. What is Nv here? 2 into 2 pi Mp into k bar T by h square whole power 3 by 2, right? This is e power minus of minus Ef and this is e power minus Ef, both will be cancelled. And what will be the rest of the term? That is e power minus of Ec minus Ev by kT, right? Now Np equal to, you know here in this expression 2 is constant, 2 pi is constant, Mn is constant, k bar is constant, S square is constant, right? Here also same, right? Here I can replace the all constants with a single constant actually, that is A naught. A naught. Here A naught is a constant which is independent of temperature. A naught is a constant which is independent of temperature. Right. Now what will be the rest of the terms? T power 3 by 2, T power 3 by 2, that is simply T cube, right? What is the value of Ec minus Ev? Actually Ec minus Ev is nothing but Eg, energy gap, by kT, right? Now here, what is the condition actually for intrinsic semiconductor? Actually N equal to P equal to Ni, right? That means what should be the Np actually? Np is nothing but Ni square. Ni square equal to A naught into T cube e power minus Eg by kT, right? This is the expression to calculate the intrinsic concentration in a semiconductor, right? Now this intrinsic concentration will depend on what actually? Here this A naught is a constant which is independent of the temperature. That means here the intrinsic concentration will depend on the two factors actually from the above expression. One is temperature and another one is energy gap. That means Here again this energy gap will depends on what actually this energy gap will be depends on temperature. That means intrinsic concentration directly or indirectly depends on what actually temperature. Okay. As temperature is increased, what about the intrinsic concentration actually increases in case of semiconductor? Right? If you increase the temperature, the intrinsic concentration will be increased. Okay. For example, for a given temperature, see for a given temperature, what will be the Ni square value? Ni square equal to constant. That means Np equal to Ni square, which is equal to constant. That means, here the product of electrode concentration and the whole concentration is equal to square of intrinsic concentration or constant is called as what? Mass action law. What it called as? Mass action law. Right. Copy? Yeah, first write down definition of intrinsic concentration. First write down. It is the concentration of free electron concentration or whole concentration. That is N equal to P equal to Ni. N equal to P equal to Ni. Right? Yeah. Copy the derivation completely. Yeah. Completed? Next topic. Calculation of intrinsic Fermi level. In bracket EFI. The next topic, calculation of intrinsic Fermi level, EFI. Yeah. See how to calculate the intrinsic Fermi level in case of intrinsic semiconductor. First, I can define for any semiconductor. For any semiconductor, what should be the electron concentration? N equal to Nc into E power minus of Ec minus Ef by Kt. And what will be the whole concentration? Nv into E power Ef minus Ev by Kt. Right? Now you can consider this one as equation 1 and this one as equation 2. Now, for intrinsic semiconductor, actually what should be the condition actually? N equal to P, right? And what about the EF actually here? EF equal to EFI. Now you can consider this one as equation 3. From equation 1 and equation 2 and equation 3, right? Here, in case of intrinsic semiconductor unequal to P, equate these two actually. That is Nc into E power Ec minus Ef become EFI by Kt, Nv into E power EFI minus Ev by Kt. Now, Nc by Nv equal to E power minus of EFI by Ev by Kt by E power Ec minus EFI by Kt. Right? Now, Nc by Nv equal to Here minus of EFI, this is minus of minus plus, it will become minus 2 EFI, right? Minus of minus plus EV, minus of EC, it become plus EC by KT. Now take logarithmic on both sides. That is minus 2 EFI plus EC plus EV by KT. So which is equal to ln of NC by NV, right? Now from this minus 2 EFI plus EC plus EV equal to KT into ln of NC by NV. What about EFI here? Actually here EFI is nothing but EC plus EV by 2 minus KT by 2 ln of NC by NV, right? This is the equation of what? Actually calculation of the Fermi level of an intrinsic semiconductor, right? But this is the equation in terms of density of energy states, right? Now here I can define the equation in terms of effective masses. See, what is the NC value in terms of effective masses? 2 into 2 pi Mn by K bar T by H square whole power 3 by 2, and NV equal to, right, 2 into 2 pi MP K bar T by H square whole power 3 by 2. So which is equal to Mn by MP whole power 3 by 2, right? Now here what about the EFI here? Actually EFI equal to EC plus EV by 2 minus KT by 2 ln of Mn by MP whole power 3 by 2, right? This is the intrinsic Fermi level in terms of effective masses, right? For example, if Mn equal to MP means if effective mass of electron equal to effective mass of hole, then what about the EFI? Actually here EFI equal to EC plus EV by 2. That means what is the conclusion actually here? See, in case of intrinsic semiconductor, actually, where is the Fermi level? Actually the Fermi level is lies in the middle of the Fermi band. Middle of the Fermi band means EFI equal to EC plus, here I am writing, here. This is EC, this is EV, this is EC plus EV by 2, this is EFI. See, exactly it lies in the middle of the Fermi band, right? Copy? Yeah. Write down last point, that is for an intrinsic semiconductor, the Fermi level lies exactly in the middle of the Fermi band. Exactly in the middle of the Fermi band. Copy this energy band diagram. Yeah. Thank you.